So the KV cache is what stops a model from rereading your whole prompt for every token. Beautiful. But that cache has to live somewhere, and at scale, it will not all fit on the GPU. This is the lesson about what happens then. And it starts with one subtle idea that changes everything. The KV cache is not stored data. It's not an archive you occasionally look up. It is working memory. Here's why that distinction is everything. During generation, the model rereads the entire cache to produce every single token, not once, constantly, hotly. For every token, it emits, which means where the cache sits doesn't just decide whether it fits, it decides your latency. And the pressure shows up fast. A 7 billion model on a modest GPU might have room for around 90,000 tokens of cache. Fine for one user. Now serve many users or one user with a huge context, and that budget evaporates. So when VRAM fills, you don't drop sessions, you offload. You push the least active cache down a hierarchy where each tier is bigger and slower than the last. Tier 1 GPU VRAM, around 3 terabytes per second, the only place fast enough for live decoding. It's small, tens of gigabytes, and your active sessions belong here. Full stop. Tier 2 CPU RAM, much bigger, but it crawls over the PCIe bus, roughly 60 times slower. Perfect for sessions that have gone idle. Park them here, promote them back when the user types again. Tier 3 local SSD, huge capacity for long idle sessions, slow enough that you would never ever decode directly from it. Tier 4 networked storage, this one's for durable stuff. Logs, checkpoints, recovering a session after a restart. Not live inference. Its bandwidth would stall generation cold. So the rule of thumb writes itself: active cache in VRAM, idle cache offloaded down. Never decode live from network storage. Now there's a competing option, and it's worth understanding. Instead of offloading, you could just drop the cache and recompute the prefill when the session comes back. Which one wins? It depends on the prompt. Reloading a long context from RAM is often far cheaper than rerunning attention over thousands of prompt tokens. So offloading wins for long prompts. For short prompts, recompute is simpler and just as fast. And the real serving stacks, VLLM, SGLang, they implement both and choose based on length and pressure. Here's a trap to dodge. This is not the same thing as PagedAttention. PagedAttention solves fragmentation inside a tier, packing the cache into neat blocks so VRAM stays tight. Offloading solves running out of the tier entirely, moving cache across VRAM, RAM, and disk. They're not rivals. Modern servers do both. Paged blocks inside each tier, tiered placement across them. Step back and the mental model is just a pyramid. Bandwidth at the top, capacity at the bottom, and you're constantly trading one for the other. Active sessions ride the fast air. The moment they go quiet, they spill downward. The moment they wake, they climb back up. And that promote on activity dance is almost always a better deal than evicting the cache and paying to rebuild the whole prefill from scratch. So that's the whole thing. The cache is working memory, so its tier sets your speed, VRAM for active RAM, for idle, disk for cold, network for keeps. Get the placement right and you buy yourself two things you can't get any other way: more concurrent users and much longer context.